All right, the welding arc. Last class on Thursday, and I felt it was a very heavy class. We discussed what the hell is this bright spark we see when we're doing arc welding. And we said, well, the bright spark is a plasma, which is a very hot gas that is so hot that is conductive. Let's see. And why is it so hot is because the current that goes through it does resistive heating. And this heating goes out in the form of radiation. And because this combination of electricity with this combination of electrical currents with magnetism creates a force, and the force made a very fast flow of the plasma. So fast that is faster than a jet plane, right? And that also makes heat exchange by convection, right? And that's how the energy is transmitted in the arc, by convection and by radiation. And then we said the arc has three parts. Has the arc column, that is what we see, and then it has an anode fall and a cathode fall. The cathode is the negative part of the circuit, and the anode is the positive part of the circuit. In the case of TIG, the electrode is negative, therefore it's a cathode. In the case of MatE, the electrode is positive, typically, therefore is an anode, right? Funny names, but eventually this is part of the dictionary we are learning. And we saw that the voltage in the arc is not like all proportional to the arc length. There is a significant amount of volts that are associated with the cathode, and significant amount of volts associated with the anode, and another amount of volts associated with the arc column. We also talked that all anodes are the same, but cathodes are not all the same. And there are two types of cathodes. They are the thermionic cathode and the non-thermionic cathode. And thermionic cathodes are those that are associated with refractory metals, which can reach very high temperatures. And at very high temperatures, before evaporating or before melting, at those very high temperatures, they can emit electrons on their own. That's the case of tungsten. That's the case of TIG. Then when the cathode is not a thermionic material, like not a refractory material such as steel or aluminum or pretty much everything else, then the cathode is non-thermionic, and it becomes very, very different in its physics. We're going to treat it in a similar way, but instead of the electrons coming out on their own, now the electrons come like lightning rods between the non-thermionic cathode and the anode, right? And it happens so fast that we barely see it. But I showed you a video in which you get to see some shimmer in the weld pool of MIG that was associated with these cathode spots, right? And this non-thermionic cathode, in which the arc attaches like lightning, is like a lightning and attaches to very quickly to different parts of the plate, typically where it can see oxides. That's what does the cleaning in aluminum, right? Like when we do TIG of aluminum and we do electrode positive, the plate is negative and it's a cathode, and it attaches the lightning rods and it cleans, it attaches the lightnings and it cleans around the weld pool. So now, for all those things we talked, I'll boil them down to this one slide. So I talked many things because I really wanted to share some of these fundamentals. Complexity I discussed, that is actually much more complex. I myself still trying to learn all this. And I just got a sign of unstable connection. So if I get lost at some point, please let me know on the chat. So to put this in context, I made a few simplifying hypotheses that are not in any book, that are only on this class. But if you use these numbers, you're going to get pretty amazing results. These numbers are not perfect. And I suspect that as I know more, these numbers will change little by little. They have changed over the years in the class. But if you take these numbers that are in this slide, which I'm going to go over soon again, you can calculate things like penetration, deposition rate, voltage, like arc efficiency. Once I was asked, how much radiation does the arc generate that can damage polymers with ultraviolet? I used these numbers, and I was pretty much on the money. So these numbers are based on the hypothesis that the voltage in energy deposited at the electrodes, right, at the cathode and anode, and the voltage that we would measure electrically are the same. But they're not exactly the same. I don't know how different they are, but they're not very different. So when I say things like the anode is 4.8 volts for steel, I'm going to say that generates 4.8 volts times current of energy on the anode. And I'm also going to say that I have to add 4.8 volts to the voltage of my arc. This is fairly abstract, so we'll discuss in concrete. So what is this summary? The voltage in the arc column is 0.8 volts per millimeter in MIG, more or less. This is not exact. This has not come from my fundamental equation, but it's what people have seen consistently. And by the way, I presented this for people of industry doing R&D to design machines, and they said this is dead on the money. So perfect. So good. And 1 volt per millimeter for TIG, in both with argon shielding gas. Helium gives you higher voltages, but I don't know how much higher yet. We have everything to measure this in our lab, everything. It's just like our lab is closed now, but if you're ever curious and you'd like to make better numbers, we can do them in our lab. So, and this 1 volt per millimeter, this is what the physicists have told me they calculate with their simulations and in their experiments in plasma physics labs. So these two numbers, they're reasonable, fairly reasonable. For the anode, right at the anode, in the space of nanometers, we have a voltage of 4.8 volts for steel, more or less, or 4.2 volts for aluminum, more or less. But we're going to use these numbers because we have nothing better. So if I were to have 100 amps, how much power is in the anode of a steel, right? Typically in MIG, for example, the anode would be the electrodes, and at 100 amps multiplied by the voltage would give us 480 volts, 480 watts. And those 480 watts are what melts my wire, right? That's how we are going to discuss later. We calculate the deposition rate. If it is TIG, the anode is the plate. And if I have 100 amps, 4.8 volts times 100 amps is 480 watts that are melting the plate, right? Cathode. If I'm in TIG, the tungsten sees more or less 1 volt. If it is exact, I'm not too sure, but it is more or less like this, right? And the numbers are fairly reasonable, we get with this. Because in thermionic, the voltage drop is relatively little. The non-thermionic, the one that is not for refractory materials, the one in which the electrons don't come out just on their own, but you have to rip them out, the voltage is much higher. It's, let's say, argon CO2, so of the order of 13.5 volts for the non-thermionic cathode, or 11 volts for non-thermionic cathode in pure argon. Just planting some seeds, look at this. If I have 100 amps, just as before, in a non-thermionic cathode, in a argon CO2 mixture, we would have 1.38 kilowatts of energy. The non-thermionic cathode has a lot more power. So just having said this, I want to pick your brain, and that will help you put a few thoughts together of things we have been discussing. But I have this question for you. Let's say I have the same current, but I have one MIG process running as always in electrode positive. And then with the same current and the same equipment, I flip the polarity and I have 100 amps, but running on electrode negative. And my question to you is, in MIG, I don't control the current. I control the voltage. Let's say the voltage will be the same, and I control the wire feed speed. Which one of these two processes, the electrode positive or the electrode negative, which one of these is going to need more wire feed speed? Which one of these is going to give us higher deposition rate? I'd like to hear your thoughts. Haha. Okay, I have one. Okay, what is reverse polarity? You have to define electrode positive or electrode negative. Because I think you, okay. So I agree. Electrode positive, no, electrode positive, okay, that's reverse polarity. No, the one that is going to have a higher deposition rate is electrode negative. Because, oh, okay, reverse polarity is electrode positive. Yeah, but that's why I never use this term reverse polarity or direct polarity. Electrode negative is going to have higher deposition rate. And the reason is that the cathode fall voltage is more than twice as high. And that means we're putting, when the electrode is negative, I'm having more than double the energy going into the electrode. I need to more or less double my wire feed speed. Otherwise, I'm going to burn all the wire into the contact tip, right? This one slide is extremely powerful because you can make all those inferences. And finally, I add something here in which I say very roughly that the electrode gets very little energy from the arc. It's true, the electrode is surrounded by, is in the middle of the, at one end of the arc, but the electrode is small, doesn't see that much action from the arc. The plate sees all this hot plasma coming into, regardless the polarity, the plasma always moves from electrode to plate. And the plate, I'm gonna call it about a third of the arc energy, right? And the energy, the arc column energy. And for the arc column, I would do these volts per millimeter times the length of the arc, let's say is TIG. And we have 3 millimeter arc length. So 3 millimeter arc length at 1 volt per millimeter is gonna give us 3 volts. And if it was 300 amps, if it was 100 amps, that would be 300 watts. And of the 300 watts of power generated in the arc column, I'm gonna say 100 of those goes into the plate and 200 get lost in the air. All right. Let's get serious. Here, we have, this is the type of problems you should expect in the quiz, in quiz 3. For example, let's say we're doing a TIG weld, and the arc length is 3 millimeters, right? And I'm saying that that right now the bead is about 6 millimeters wide, and I'm assuming that the bead and the arc are more or less the same width. Not exactly true, and we have the formulas to say it exactly, but let's not worry about the exact right now, but let's get a general understanding. Number one question, if I have a TIG arc and the arc length is 3 millimeters, what is the voltage? This is an amazing question. This amazing book you have of the procedure handbook of arc welding, the Lincoln book that is mandatory textbook. In that book for TIG, they don't give you the voltage in TIG. If they don't give you the voltage, how are you going to calculate a heat input? Well, typically, if you're just going to get it done, you don't need it. But let's say you want to understand, you want to troubleshoot. You'd like to know, is this a big heat input? Is this a small heat input? But because you took this class, you're gonna say, all right, let me think. The welding voltage would be the voltage of the cathode plus the voltage of the column plus the voltage of the anode, because they are the three parts of the arc. And for the cathode, it's more or less 1 volt, because this is this 1 volt we have here in the previous slides. The column is 3 millimeters, and we said, the cathode is this 1 millimeter here. The column is 1 volt per millimeter times 3 millimeters, and gives us 3 volts. And then we have the anode, and the anode is more or less 4.8 volts. I added it all up, 8.8 volts. And you know what? If you go and weld, I'm sure you will not measure exactly 8.8 volts, but what you measure is not gonna be all too different. And this is what is amazing here. So these numbers I have, I've been like over the years tweaking them as I find more and more information. And this is more or less right. Perfect? No. But for example, recently I got a paper from China on variable polarity TIG welding, very advanced for aerospace. And the guys do all these experiments. And then they say, well, this is the voltage we measure. As you know what? It's pretty much dead on what I can calculate with these numbers you're having from this class. I'm happy with that. All right. Arc width. So in one of the previous slides, I mentioned something that is not in any book, but I know because I have worked on this and we have published papers. The width of the arc is more or less proportional to the square root of the length, right? And actually, we have one super awesome student visiting us from Chile who was working on much of this modeling. So the width of the arc is more or less proportional to the length of the arc. Not exact again, but so if I have two different arc lengths, let's say L2 and L1, the width of the arc, let's call it W2 and W1, would be like the square root of that. So I can calculate what is the new length of the arc as solving for L2 from this equation. And I would have then, yeah, the 3 original millimeters. Now I wanted to have a 7 millimeter arc width compared with the one I had before. I do this calculation, gives me 4.1 millimeters, right? Exact? No. Approximate? Yes, very much. And nobody can tell you this from a calculation. It's not in any book. Either in welding, you either know or you don't know. Except if you take this class, then you can think things you haven't done before. That's the whole point. And guess what? So if I increase my arc 1.1 millimeters at 1 volt per millimeter, that means 1.1 volts more, and the voltage of the arc goes from whatever it was 8.8 to 9.9 volts. This is pretty awesome. And now you can calculate heat inputs with this, right? But we can do even better than that, because when we discuss arc efficiencies, we're going to see that efficiency also changes. But the books, they give you a very broad range of efficiencies. We can calculate something that is a lot better because we can account for how the efficiency changes with different conditions. So what I have done in these couple slides is something that no book can tell you, but you will be able to do, to calculate a voltage of a welding process by knowing some parameters that are the part of the essential variables, and then calculate a parameter that is not listed. That's powerful. Another example, I'm doing TIG, and then I will move to discuss MIG very soon when we discuss voltage in arc welding. So let's calculate the power in TIG when we are at 150 amps, and the power at the electrode and at the plate, right? And in this calculation, in which I'm going to go very quickly because you have it uploaded and you can go over that in detail yourselves, then we can calculate if it is electrode negative, we have current times voltage at the cathode, that's for the electrode, and how much heat the arc gives to the electrode, which we said this is nearly zero. So here we have 150 amps, that is the current we have, times 1 volt in the cathode, because we know it's a thermionic cathode, plus no contribution from the arc, and that gives us 150 watts at the electrode. If we do similarly for the plate, is now the full voltage is 4.8 volts, that is in a table, right? And in addition to that, we want to add an approximate calculation of how much of the hot plasma gets transferred, how much of the energy of the hot plasma gets transferred to the plate. That is 1/3, more or less. And with this, we calculate then 920 watts. So keep these two numbers in mind: 150 watts at the electrode, 920 watts at the plate. If I flip the polarity, right, in this case is what would be called reverse polarity now, right? Electrode positive, the way you don't want to do it because you melt the electrode. And what do we see? Now, if the electrode is positive, the electrode is an anode. And if the electrode is an anode, has a full voltage of 4.8 volts, and no much contribution from the arc on the electrode, and we get 720 watts at the electrode. Let me show you what we were before. Electrode negative, 150 watts. I can dissipate those either through the air or with a water-cooled torch, no problem. I flip the polarity, 720 watts. Well, let me tell you, you don't dissipate 720 watts with just a water-cooled torch. You melt the electrode. I tell you a very funny story. When I started my PhD, I went to Oak Ridge National Lab for a good part of a summer to do a set of experiments aimed to doing modeling of TIG welding. And because I wanted to be very scientific, I said I want to do all the velocities I can do, all the currents I can do, all the arc lengths I can do. I want to do both polarities. And the technician said, no, you don't do positive electrode in TIG. And I said, well, if for the sake of science, we're going to do it. He said, but you shouldn't. I said, I want to do it. Well, you want to know what happened? The technician melted the electrode and told me, I told you so. And of course, now that would not happen to you, but it did happen to me. And I looked pretty foolish back then. I wish I had notes as good as the ones you're getting. So this is exactly what happened, right? Now on the plate, funny enough, the electrode had more power. Does the plate then get less power? If the electrode got more power than before, does the plate get less power than before? And the answer is no. The power gets even more power. The plate gets even more power. Why? Because before, in electrode negative, the plate was an anode at 4.8 volts or if it is 4.8 volts. And but now with the electrode positive, the plate becomes a cathode at where is it? At 11 volts, right, of cathode fall voltage, right? This is for pure argon, right? It's a lot more power. We went from having 920 watts to having 1850 watts, more than double, right? This is interesting. And here I have a calculation I will not do right now, but you have it. What happens if it is 50% polarity? Now, let me tell you something interesting. If you look into the amazing book of the Lincoln Welding Procedure Handbook, it says that TIG with electrode positive gives you less energy. Well, that I know for sure is not true. I don't know why they say that. Probably they saw something that I don't fully understand yet, right? So that book, which I love and I suggest that you buy, tells you many important things, but some of those are a little bit off. Funny enough, people in our university have measured that. MatE is a very well-known welding engineer in our province, and Barry Patchett is my predecessor. I had nothing to do with this paper I'm showing you here, but they show here the weld penetration. This is a paper in the Welding Journal, and they show weld penetration as a function of electrode positive in TIG. And guess what? The more electrode positive you have, if you have variable polarity, right, the more penetration you have, because you have more time to plate as a cathode, right? And does frequency matter? No, unless you get into the transient of the arc, frequency doesn't really matter, because all you're doing is, or as long as your machine responds fast enough, having the same combination of the same two things, just like whether you hash it finer or coarser. Very, very interesting. These friends wrote a whole paper and did a lot of experiments for something that now I just, you could anticipate from the formulas in the class. Powerful and modern. Arc stiffness, I will not dwell into these equations in much detail, but this is a force that is created by the current at the arc. So it's as if you had a force pushing the plasma, and the velocity of the plasma you can calculate quite well with this equation. Mu0 is the magnetic permeability of vacuum. I is the welding current. JC is the current density of the electrode, and rho is the density of the plasma. How good is that formula? Well, this formula is the one that predicts more or less 300 meters per second in welding. And you can even extrapolate this formula for welding, electric arc furnaces, in which you're welding at more than 1,000 amps. And in this graph, what we see is welding current in the horizontal axis and the maximum velocity in the axis of the arc. And the little circles, they are this formula. And the triangles are numerical simulations of a guy who did his PhD at MIT in the early 2000s, and each simulation would take about a day. I would say the formula is not that bad, right? This velocity is what gives the arc what is called the stiffness, right? About arc temperature, we have in this schematic, this is part of the simulations of this arc. And we have, if we look along the central axis of the arc, we see that the arc right in contact with the electrode is not too hot. Let's say it's of the order of 3,000 Kelvin. That is the temperature of the tungsten. And if it is in MIG, both steel and aluminum, the droplet is at about 2,500 C, right? And then it reaches a peak, right? This direction I'm indicating here is the axis of the weld, and this in this direction from here, from right to left, is temperature. and we have a peak at about 20,000 Kelvin for TIG. I put 10,000 for MIG, but in reality, it's of the order of more about kind of 15,000. We'll discuss this better in other slide. But in TIG, you see this peak, and then it more or less maintains until it reaches the plate, and it cools down very quickly. If we look at a cross section of the arc, we're going to see the plasma in TIG. This is for TIG. The plasma in TIG, and it's very different than MIG. The plasma in TIG is hot in the center, and then it cools down towards the edges, right? To some extent, the geometry of the temperature distribution is fairly simple. It's not a crazy distribution with turbulence. It doesn't go up and down. In TIG, very straightforward. What we have here is a balance between the physical mechanisms that are in the arc. So there are 5 physical mechanisms in the arc. One is conduction, one is convection, which we know, one is radiation, which we know. There are 2 more. One is Joule effect, that is heat generation by the effect of electrical current. And the last one is Thomson, that is heat transport when you have charged particles in an electric field. So electricity moves the particle because it's electrical, but the particle brings electricity. Let's not worry about Thomson effect. That matters almost only close to the electrodes, and it's not such a big deal for us. But what we see here is that close to the electrode, we have a balance between Joule heating. This orange thing means Joule heating is generating heat, and the heat is getting out. On the right, we're indicating how the heat goes out. So what is on the left says what mechanisms bring heat in, and on the right is out. So, oops. Here it says that next to the electrode, the heat comes in by Joule heating and goes out by advection or convection, right? Like the motion of the fluid. And other parts, for example, here in the middle, you have so Joule heating causes heat, and it goes out mostly by radiation. And then down here in this little bell-shaped part, we have that the heat is coming in because of convection. This is hot gas that is losing energy by radiation. And down here, we have a classic boundary layer. Those of you who took the heat transfer class, it all comes together. Here we have a boundary layer in which the heat comes in because there is a hot fluid coming in, and the heat goes out by conduction to the plate, right? So we see how the arc has these different energy heat transfer mechanisms, all that play simultaneously, but in some parts is more important than others. And here in the outer region of the arc, we also see that the heat input is by Joule heating, and the output is by advection. So this is for the TIG arc, and this applies to pretty much every current. And we know that this is also true for argon and helium. Let me tell you about the MIG arc. The MIG arc is a very different animal. It looks the same. It looks different when you look at it, and but it should be the same because it's still like current going through ionized gas. So in MIG, we have the wire, we have the droplet, and what we see is that the arc has two parts. One of the parts is an inner part that is very bright. And here's the main difference between TIG and MIG arcs. In a TIG arc, pretty much the whole plasma is the ionized shielding gas, typically helium, argon, or a combination of those two. That's it. In MIG, even if you have pure argon as a shielding gas, if you were to have pure, the droplet gets so hot that it's near the boiling point and starts to evaporate metals. And the strong jet that is generated in the arc, the strong jet carries these vapors down. This is super cool, but this has enormous consequences. If you remember, when we talked about metallurgy, we talked about how the iron carbon diagram is an approximation of real steels, but real steels have more or less 1% manganese. And the reason is to deal with the sulfur and phosphorus that is inevitable in a normal casting process, in particular sulfur. Okay, now it so happens that manganese has two very interesting properties. Number one, manganese, when it gets into your body in the wrong way, causes a disease very similar to Parkinson. It's called manganism. And it's super bad. And there have been enormous lawsuits. By enormous, I'm talking about like comparable to the tobacco lawsuits, right? About manganese in the welding fumes. The other property of manganese is that it evaporates much more than stoichiometrically. So if you have more or less 1% manganese in your electrode, the fumes can be up to 50% manganese. That's a lot, right? So these things we're discussing here are topics of super high interest for the companies making machines and electrodes, because reducing manganese is essential. The health and safety organizations have levels for how much manganese is tolerable. Recently, they have lowered those thresholds for how much manganese you can have in the air to 10% of what they used to be, a factor of 10 in reduction. Most welding processes that were working fine don't work fine anymore, according to that threshold. What are you going to do? Put your welders in a spacesuit? Maybe. Okay, I have a question here about estimate of energy used for phase changes. The phase changes happen in two places. One is in the plate, and the other is in the electrode. In both, you involve melting, and in the case of steels or titanium, you also have solid state phase changes. From the point of view of the deposition rate, the amount of energy consumed by those is very easy to account. From the point of view of the plate, we're going to see formulas to calculate temperature on the plate. And in all those cases, we assume that the latent heat of phase transformations is distributed evenly in the through the whole transformation, not that it happens all at the same time. If you neglect the phase transformations in the solid, your calculations are more or less the same. If you neglect melting temperature, you're a little bit off, but not a whole lot off. But right now, I'm focusing only on what happens in the arc, and we'll discuss electrode and plate later on. So this is a super awesome experiment done. They did tomography of the MIG arc. So to do this, they have, I believe, 6 high-speed cameras looking at the arc all around it. It was a crazy experiment done in Japan, in Osaka. This is by Professor Hirata. But look at this. Blue is cold, yellow is hot, and red is super hot, right? I mentioned that the inner core of the MIG arc was bright, was very bright. But these people measure the temperature. And what did they got? That the core of the MIG arc is cold, more or less 5,000 Kelvin. That's very cold for a plasma. If it was argon, it's not even conducting electricity. But it's not argon. Right here at the core, we have the metal vapors. And these metal vapors ionize much easier because metals conduct electricity already. They don't need to be vaporized to conduct it. So the generation of current is much lower here. And then the amount of metal vapors is lower on the sides. and the arc then has all the proper resistance, and it gets very hot. Very different in MIG arc than a TIG arc because of these core or metal vapors. So look at this. These are experiments done here in Canada at the University of Waterloo. It's an amazing project in which they use, inspired on work done in Japan, they use narrow wavelength, narrow pass filter, wavelength filters for the cameras. So in the plasma, things radiate. You see like a spectrum with your eyes, but in reality, there are some particular wavelengths in which things are emitted. So there's a wavelength that is good for argon, that is this at 695.5 nanometers, and another wavelength that is good for iron. So if I look into the wavelength of argon, I will see only the argon. If I look at the wavelength, it's like the color, right? Like having color filters. If you look, I look only at the color of the metal vapors, I will see only the metal vapors. I see what they saw. This is amazing. This is globular transfer. And the red is when they are using the wavelength for argon. And they see all this in the argon. See, very bright here, but it's not so bright in the middle. That means there's not so much argon there. Then they looked at only the color of the metal vapors and see, these two are the same weld. You see how the metal vapor is coming as a jet. You see, this is the bright spot in the arc. It's not hot, it just happened to emit a much more visible light. The metal vapors emit much more visible light, even at low temperatures. This is for globular transfer. This is for spray transfer. Very much the same. See this shower. This is a shower of metal vapors. What is the consequence of the metal vapors? Well, one, if it is manganese, some of that is in the air and you don't want to breathe it because it's in the fumes. That's why we have these snorkels and all kind of respirators and all kind of ways of capturing the welding fumes, which we discussed at the beginning of the class. Number two, this is what, in the case of aluminum alloys, there is a similar effect to steels, but with aluminum magnesium. And magnesium evaporates a lot. And magnesium then oxidizes, and all these magnesium vapors deposit in the form of a black soot, which they call smut. And a high alloy magnesium, high magnesium alloy, and aluminum with a high content of magnesium looks horrible after you weld it because it's all black. And then you have to clean it up. So is there a way in which we could reduce these magnesium vapors, right? And have less of this smut? Very interesting things, right? That relate to the different plasmas. The temperature, if I make a cross section of the temperature of the arc in MIG, I would see the temperature goes high and then has a dump, dips and has a bump down in the middle and goes up and comes back down like a camel hump. It's a very different temperature distribution. All right, so much for the welding arc. I would like to switch to voltage in welding. Any questions while I switch slides?